Okay, we're back on the air for another installment. So homework 2, calculation of the expected value for the birthday problem. That's due on Thursday. That's pretty easy. Any questions about that? Should take 15, 20 minutes. Yeah.
Get like 22,000 consistent.
You probably made a mistake.
Something with my accumulator, the summation of everything. I'm not sure, first notes in class, I'm not sure that what you made was.
Did anybody do it?
I did. I got 24.6 something.
Okay, that's right. And you did it the way I did it in class, right?
Yeah.
Okay. So I'm innocent. He did it the way I did it in class and got the right answer. It's about 24.6, 24.6 something.
That's what we expect.
Right. So it's probably, well, either you've got the algorithm copied down wrong or it's a programming error.
We only have to run one simulation, correct? We don't have
It's
to.
not a simulation, it's a calculation.
Calculation.
It's important to understand the difference. What you did in homework 1 was a simulation,
Okay.
which was an artificial experiment using the computer's random number generator.
Okay.
And what you're doing this time is you're doing a theoretical calculation. So you run it once, and you get one number, that's the answer. Okay.
You said we should state the algorithm in mathematical notation. You want us to just give you back what you did?
Yes, right. Yeah, typically what students do is they write the program, and then they show the answer. But that may be good for your benefit because you're writing the program. But if you look at it a year later, or if you gave it to somebody else, then it would be very hard for them to figure out what you were doing. So in fact, what you should do is you should write the algorithm in mathematical notation, which is sort of a conventional, traditional language. And everybody understands that. And then the program is simply an implementation of that, and there are various different languages. Of course, in this case, it's no big deal because I already did it, but that's what you're supposed to copy over on the cover sheet. Anything else? Okay, so we're getting to the heart of the course now. I think I started discussing this last time, the Poisson process. Okay, so Poisson process. The idea is this. We have this process in which events occur randomly in time. And so we have to define exactly what we mean by occurring randomly in time, and then calculate a description of this. So at this point, it will merely be a description, so you could say, so what? But shortly we'll actually use it in calculating other things that are more meaningful. So here's the idea. Imagine that some random process occurs. So let's say here's time 0, and then an event occurs. And I'll indicate that by an arrow. And then sometime later another event occurs. And then later another event. And these events occur at random, whatever that means. And the question we want to ask is, what's the elapsed time between these events? So for example, I can call that x1. That is, x1 is the time between start and the first event. And then x2 would be the time between the first event and the second. And x3 and so forth. So there's a generic random variable here, x, which is the time from an event until the next event. We want to be able to calculate the distribution, or that is distribution function or density function of this random variable x. Now, we have to make some assumptions here, because remember what we're making is a model of physical reality. So the example that's often used in the textbooks is radioactive decay. So what you have is you've got some mass of radioactive stuff, and you have a Geiger counter, and then every once in a while you hear a click, which represents the decay of some electron or something or other, some fundamental particle. You have a click, and then there's a delay, and then another click, and then another click, and so forth. So you could say, how can I describe the process, what's happening with these clicks? And you might say, from a probability point of view, you would say, well, basically what this says is that every instant in time is just as likely to have a click as every other instant. There's no reason why the radioactive decay, the Geiger counter clicks, tend to favor one time over another. And the second thing you might say is that these times should be independent of each other. That is, if you've got a gigantic number of elementary particles that are decaying at random, then you wouldn't expect that if a click occurs, the time at which it occurs is statistically related to the time at which the last click occurred, or the time the next click is going to occur. In other words, there's no memory in this process. The radioactive decay doesn't remember when the last particle clicked, and so the process should be such that each instant is just like every other instant, and they're independent of each other. Now, not only would this describe radioactive decay, if I can come up with this description of the X's, but it would describe anything, any process that has the property that events occur randomly in time. Every point is just as likely as every other point to have one of these events, and the points are independent of each other. So if I make those assumptions, then regardless of the physical thing I'm describing, if those assumptions are met, then the description of the X's should be exactly the same. So not only would it agree, or would it describe radioactive decay, but these instants could be, for example, they could be the times between, say, some kind of disaster, like accidents on I-95, for example. Or these could be the instants or the times separating successive times at which a commercial airliner crashes. So this time scale would be different. For example, if you're talking about radioactive decay, then these intervals might be measured in seconds. But if you're talking about crashes on I-95, maybe then the intervals are measured in hours. If you're talking about crashes of commercial airliners, maybe the intervals are measured in years. But nevertheless, it's still the same argument that whenever one of these events occurs, it's just as likely to have occurred one instant as any other instant, and there's no connection between them. Now, that's not exactly true if you're talking about airliners, for example, because at least prior to 9/11, the safest time to travel on a commercial airliner was just after you had a crash, because then everybody's careful. But other than that, there's really no effect. These are all independent trials because there's millions of takeoffs and landings each year, and almost all of them are successful. So every once in a while you have this random event and a plane crashes. So it describes fundamental things like radioactive decay. It describes sort of man-made things like accidents. I don't know if that's really man-made, but it's certainly different than radioactive decay. Maybe you're sitting someplace in the universe and you're going to peer out and you're going to look for stars. And so as you start looking here and you have some kind of line of sight, there's going to be some length of time until your line of sight is interrupted by a star or something. And then if you could see beyond that, there would be another time interval, or distance interval in this case, until your line of sight would be interrupted by the next star, and so forth. So if it made sense, if the stars were distributed in the universe in such a way that you could say that along your line of sight, every position is just as likely to be interrupted by a star as every other position, and they are independent of each other. Of course, the stars can't be too close to each other because they would physically overlap, but on a cosmic scale, there's mostly space out there. So you could say, well, maybe this fits the same model. And if that's true, then this random variable that I'm going to get, these x's, would also describe the distances between stars. So in effect, you could say it describes almost everything. In fact, one of the examples I like to give is, suppose that this represents a path, and cows walk along this path, and they drop patties here. And every once in a while, as you walk along the path, you see a cow patty. And then you say, well, a cow patty is as likely to be at one spot as any other spot, and the cows are not worrying about where the other cows do their stuff, so everything is independent. So therefore, the distances between the cow patties should have the same distribution as the time between clicks on a Geiger counter as the distance between stars in the universe at the time between crashes on I-95. This connects everything. So once you understand this, you could argue, you could claim that this lecture alone is worth the price of the course, even if you're paying out-of-state tuition. So this is a good one. Of course, I'll probably say that again later with the next topic, but this is very important. Okay, so how am I going to make this model? So here's what I'm going to do. I'm going to divide time up into little intervals. And so I'm going to start with time being discrete, and then I'm going to pass from discrete time to continuous time. So let's say that here's some time t, and there are n intervals, so interval number 1, interval number 2, interval number n. And each interval is of the same width, so each interval is as likely as every other interval to have an arrow, to have an event. And whether or not an event happens in any interval is independent of what happened in any other interval. So it's exactly what I'm talking about here, except that instead of points, I have little tiny intervals. Because remember, the probability in a continuous process of having an event occur at random at any particular point is 0. Okay, so let's say that here's some arrow. Let's say for the sake of this derivation, that's the first arrow, which means that this distance here would be x. And the question I want to ask is, what's the probability that x is greater than t? Now, I'm asking it as greater than just for convenience, because the distribution function is defined as the probability that x is less than or equal to t. But it's more convenient to calculate this and then subtract from 1. So in other words, the probability that x is greater than t is 1 minus the probability that x is less than or equal to t. In other words, 1 minus the distribution function. So if I can calculate this, of course I can calculate capital F. Okay, so now we want to calculate the probability that x is greater than t. So now I say, all right, what I'm going to do is imagine that this x has occurred, this event has occurred in one of these little intervals, and let's say that the probability that it occurs in any interval, that is, let me say this again, the probability that any little interval contains an arrow is p, and the probability that any little interval does not contain an arrow is 1 minus p. So in other words, in every interval, which is going to shrink to an instant, either you have an event or you don't have an event. So if p is the probability that an event occurs in a little interval, the probability that the time from now to the first interval, first event, is greater than t is the probability that there is no arrow in interval little interval 1, and no arrow in 2, and no arrow in 3, and so forth. So what's the probability that there is no arrow in the first interval? Well, all intervals have the same probability of an arrow, so the probability of no arrow is 1 minus p. What's the probability of no arrow in the second interval? Well, it's the same thing, because all the intervals are statistically identical. So the probability of no arrow here is 1 minus p, and no arrow here is 1 minus p, and so forth. So what's the probability that there is no arrow in all n of them? If the intervals are independent of each other, then it would be 1 minus p times 1 minus p times 1 minus p, and so forth, multiplied by itself n times. So the probability is 1 minus p raised to the nth power. But now n is the number of intervals between 0 and t, and if I want those intervals to go to the limit as points, then if I take n going to infinity, that means that between 0 and t, the width of the intervals must go to 0. So I'm going to take the limit of this as n goes to infinity. Okay, so for any particular p, as n goes to infinity, of course, this is going to go to 0. And so I'm not finished with my argument here. As the number of intervals gets larger, that means that the width of each interval gets smaller. And if the width of each interval gets smaller, then the probability P that an interval contains an arrow should also get smaller. And as the width of the interval goes to 0, the probability that the interval contains an arrow should go to 0. So we'll let n go to infinity and P go to 0. But this can't be arbitrary. Somehow or other, the n and p have to be connected to measurements. Because remember, this is going to be able to describe radioactive decay or times between disasters or distances between cow patties. So if I have the same law, the only thing that's going to differ in each case is the scale. So what I need to do is somehow or other connect the scale of things to these numbers right here. So I'm going to do that by calculating, in theory, the expected value of the number of arrows you would expect to get in the interval between 0 and t, and then count them and then equate the two. So let's look at the theory first. On average, how many arrows would you expect to get between 0 and t if the number of trials, you could imagine that a trial is like tossing a coin. And each time I toss a coin, on the coin I have written down on one side arrow, on the other side no arrow. And the probability that the face of the coin that says arrow on it comes up is p, and the probability that it doesn't come up is 1 minus p. So it's a weighted coin. So if I'm going to toss this coin n times, and p is the fraction of times I get an arrow, how many arrows would I expect to get on average between 0 and t? If I tossed the coin 1,000 times, and the probability that on any particular toss I got an arrow was 6%, how many arrows would you expect to get? 6% of 1,000? 6. In other words, NP. So if I multiply the number of trials times the fraction of trials that give me an arrow, that's what P is. It's the frequency or fraction of these trials during which an arrow would occur. It's the fraction of intervals that contain arrows. So the n is getting bigger and bigger, the p is getting smaller and smaller, but NP, which is their product, is remaining constant. It's some average value, which is independent of my model, but depends on the physical reality. So I'm going to set NP equal to something, and the something I'm going to call lambda t. T is this time, so lambda would be the rate at which the arrows occur. Okay, so we're going to have lambda is equal to the arrival rate. So this is the part that connects this to reality. Presumably, the assumption is that I could measure this and I could see how many arrows occur per unit time. That would be the arrival rate. So another assumption in this model is that if I simply observe this over, in principle, an infinite length of time and divided the number of arrows by the length of time, I would get arrows per unit time, and that would be a stable value. Now, maybe that doesn't make any sense if you're talking about I-95, because after an infinite amount of years, I-95 isn't going to be here anymore. But in principle, you could think, say, if you're talking about decay of fundamental particles, that in principle, you could imagine this process just goes on forever, and these clicks just occur at some standard rate, even though they are unpredictable in the short run. In the long run, you could say, yeah, the clicks are occurring at the rate of 22 a minute or something like that. Okay, so I want to take this limit. So I let n go to infinity, p go to 0, but I keep the product np constant to be equal to rate times time. That's my model. Any physical process, any kind of process, for which you could make this argument, then the result is going to be exactly what I get when I take this limit. It doesn't matter now what it is that this is describing. All that matters is that these assumptions are reasonable. Everybody okay with that? So it's pretty simple. I mean, you couldn't think of a simpler possible description of events occurring randomly in time. Simplest possible thing. It's analogous to saying that if I pick a card out of a deck and the deck is shuffled, each card has probability 1 over 52 of being chosen. Same thing. The least presumptive assumption. Okay, so now I'm going to do some arithmetic. So I'm going to rewrite this as the limit as n goes to infinity. And then I'm going to replace my p by, from this equation here, I'm going to replace p by lambda t over n. I still have the n there. And now, these two things are equivalent, but this is simpler because I've gotten rid of this part right here. Okay, so now I've got to take this limit, equals. So before I do that, let me remind you, in fact, here's something that's given in the book. So let me write this down. This is standard stuff, everybody knows this. The limit as n goes to infinity of 1 plus x over n to the nth power is what? Anybody know? E to the x, right. So this is standard stuff from calculus. In fact, some people, some books, or depending on your viewpoint, could take this as the definition of the exponential function. Although usually the exponential function in elementary work is defined differently, and then it's proved that this is a true statement. In any case, in the textbook, the author says that this is, quote, from calculus. Okay, so that's the calculus you're all supposed to know. The author of the book doesn't know all the problems you had with homework 0. And this is on page 189. Okay, so we'll just take that as being a true statement. Let's see if this blue one looks better. So we'll take this as being a true statement. And I'll verify it in a moment, just because if I just take it as being a formula, then it seems to have less meaning than if you really believe it. You got to believe it emotionally, not just intellectually. But what that means is that if I plug into this formula here, this is exactly the same as that, except that the x is replaced by minus lambda t. So this answer then is e to the minus lambda t. So the probability that I have to wait longer than t for my next Geiger counter click is e to the minus lambda t, where lambda is the long-run rate at which the clicks occur. And in the derivation, we've assumed, of course, that the t is not a negative number, so I'll write that down like that. Okay, so what that means is, can I get some more of these markers in here? The black ones seem to be running out, and the blue ones you can't see very well. Markers. Okay, so let me erase this here. So what we've seen then is that this is the, that's 1 minus the distribution function, so therefore the distribution function of x evaluated at t actually has two forms. We didn't bother to derive it, but obviously it's 0 when t is negative, because you can't have a negative waiting time. And when t is not negative, it's 1 minus e to the minus lambda t. 1 minus because of that. And in that case, the x is said to be exponentially distributed, exp, that's the abbreviation, and it has a parameter lambda. Okay, so that's the distribution function of a random variable that represents events occurring randomly in time, according to this model. So this is the model, and then to get to here, from this point on, this is math. But the important thing about the math is that once I state this, which is the model, I have no choice. Once I state this, that's the conclusion, that's all there is to it. It's unique. There is no other possible answer if the conditions that the assumptions I made for the model hold. Okay, so this you should recognize as being one of the random variables that we looked at in homework 0. We looked at 2 random variables so far now that were continuous. The uniform, which we just barely scratched the surface of, we'll get back to, and the exponential, which is this, and the third one that's going to be of importance that has a name is the normal. So we'll get to that. Okay, so let me erase this. Okay, so the first thing is I can calculate the density function by differentiating the distribution function. And when I do that, if I differentiate this, of course I get the 2 branches. I get 0 for t negative, and I get lambda e to the minus lambda t for t not negative. And in homework 0, you were given this right here. You were given little f is equal to that, and you were told that big F was the integral of that, and you were asked to find it, and you got that. So in homework 0, you went from here to here, but in the derivation, to have physical meaning, I went from here to here, because you know that they're equivalent. So this is done in homework 0. Now, you also know from homework 0 that the expected value of x would be equal to the integral, because you already did this, from 0 to infinity of t times lambda e to the minus lambda t dt. That is, this is what it is for the particular case of the exponential. In general, it's the integral over all t of t times density function dt. And then in homework 0, you work this out, and it turned out that the answer was 1 over lambda. But that's exactly what you should expect now once you realize the derivation. Because remember that lambda was the rate. So we have these events occurring, and they're occurring by definition with rate lambda. So what this says is that the average value of the time separating these arrows, these Geiger counter clicks, on average, they're equal to 1 over the rate. So for example, if I told you that these arrows are occurring at the rate of 1 arrow per minute, or let's say I said this. Suppose that the rate was 2 arrows per minute, what would be the average time between arrows? 1/2 a minute. So it's not surprising that if in the derivation the parameter lambda represents the rate, then the average length of the time between these arrivals is the reciprocal of the rate. Right? If they occur at the rate of 2 per minute, then the average time between them is 1/2 minute. So if lambda is 2, which is what it was in your homework 0, then the average time between these guys is 1/2. We also found that the expected value of the square, which you worked out, that was given by this, and that turned out to be equal to 2 over lambda squared, but that was just by evaluating the integral. And from that, you could calculate, we already did this when I illustrated variance, the variance is equal to the second moment minus the square of the first moment. Or in other words, it's equal to 2 over lambda squared minus 1 over lambda quantity squared, which is equal to 1 over lambda squared. All right, so in homework 0, we've already done all the arithmetic. But all of this depends now on whether or not this limit statement is really correct. Of course it is, it's a theorem. But let me convince you that that's true. We have someone here with a calculator. Okay, so it's probably worth going through this. Although it's never, you could argue that it's never necessary to illustrate a theorem. Because if you could prove it, you don't need an example. That's what theorems are for. Okay, so let's make a calculation. Let me calculate for different values of n. So we'll take n is equal to 1, 10, 100, and so forth, and see how the limit goes. So, pick an x. Somebody give me an x. What? 5. Okay. So, if x equals 5, let's calculate e to the 5. So first of all, anybody got a calculator? Just put in exp5 and press the button.
About 148.
Okay. It's 148. Give me some decimal points.
0.413.
413. Okay, that's e to the 5. So now what I want to calculate is 1 plus 5 over n to the n. Okay, so when n is equal to 1, this would be 1 plus 5 over 1 to the 1, or 1 plus 5, or 6 to the 1, or 6. When n is equal to 10, this would be 1 plus 5 over 10 to the 10, or 1.5 to the 10th power, right? What's 1.5 to the 10th power? Got someone with a calculator out there?
57.665.
Okay, 57.665 going. When n is 100, I'm going to have 1 plus 5 over 100 to the 100, which would be 1.05 to the 100th power. Anybody got it?
131.501.
131.501. Okay, 1,000. Now I'm going to have 1.005 to the 1,000 power.
$146.576.
146.576. Okay, well, it's getting pretty close. Let's do it one more. 10,000. 10,000, it would be 1.0005 to the 10,000 power. Calculator should still be able to handle that.
148.228.
148.228. So, looks like this is consistent with the theoretical prediction. Let's do one more case, because what we're interested in here is the case where the x is actually a negative number. And so that doesn't really mean subtract. Negative number means reciprocal. So maybe it won't work. Of course, it will work, but it's still worth looking at. Let's do it again. Let me erase this one. So here is n. And let's pick a value of x, negative value. Right? 2, good choice. Okay, so we want to calculate e to the minus 2, which is, what is it? 1 over e squared? That is true.
0.1353.
0.1353. Give me some more.
35.
Okay, 135335. Is that right?
Yes.
Okay. So now I'm going to calculate 1 minus 2 over n to the n. So when n is equal to 1, this would be 1 minus 2 over 1 to the 1, which is minus 1 to the 1, which is minus 1. Not too close. When n is equal to 10, we have 1 minus 2 over 10 to the 10. That's 1 minus 0.2 is 0.8, right? 0.8 to the 10, which is
107.374.
0.107, okay? When n is 100, this would be 1 minus 2 over 100 to the 100. That would be 0.98 to the 100,
13262.
13262. Okay, getting close. Let's do one more. 1,000. Then we have 0.998 to the 1,000.
135,065.
135,065. Okay, 135. I don't think anybody doubts that it's going to get to the right answer, going to converge. So this certainly doesn't prove it, but nobody should doubt it. It's just a mathematical fact. So based on that fact, this thing must equal what I erased. Based on that mathematical fact, this thing must equal e to the minus lambda t, which means that this is the distribution function, that's the density function, that's the mean, that's the variance. This stuff is actually worked out in the book on page, some of this is on page 271. I think what's on page 271 are these calculations here. Okay, so now you know the exponential distribution. The application where we're going to use it is the following. Let's see, let me erase this stuff here. But you can see there's lots of applications. So this is, let's see here. Okay, now here's what's going to happen in our application. Suppose that we have a node in the internet, and messages are arriving. So lambda is equal to the arrival rate of messages. So you could argue that the messages are going to occur completely at random. That is, they should meet this model right here. So there's a message, there's a message, there's a message, and the only thing you know is the overall rate at which the messages occur, but you can't predict the instance at which they're going to occur. Now, you're the designer or administrator of this network. So you've got to provide the resources to be able to handle these messages. The difficulty is that the demand for the resources is random because you never know when a resource is going to be requested. Now, when it is, if this is a demand for a server, then if the demands tend to be bunched up, then you're going to have queues formed. In fact, there's two actual processes, random processes going on here. First of all, there's the instant at which the messages arrive, and then there is the bandwidth requirement of the message, because some messages are longer or shorter than others. So I'll indicate that by this height right here. So the instant at which the messages request the use of the server is random and is described by a Poisson process. And the length of time or the bandwidth requirement for which that server or resource is required is also random. So it has some other random variable that describes the demand. Then the question is, given these two random processes, that is, knowing that the arrivals occur at random with a certain rate and that the demand, the bandwidth requirement, has some particular probabilistic characteristic, some distribution or density function, then the question is, how do the queues build up? Because what's going to happen is, here's your server. So this is your transmitter, let's say. This is a channel. Okay, so I'm going to call this a channel. And the messages are going to arrive at random. And if a message arrives and the channel is available, then the message holds the channel, and it holds it for a length of time. That's the bandwidth requirement. That's random. And while that channel, while this process is going on, maybe another message arrives. Now, when this message arrives, the channel has already finished serving the previous message. Then this guy goes right in, no delay, and he holds the channel for his bandwidth requirement. But if the channel is still busy with the previous message, this guy waits on a queue. And while he's waiting, maybe another guy arrives, and another guy, and so forth. So what you want to know is things like, well, on average, how long do these messages queue up? How long do they wait? And what is the utilization of the channel? And what's the probability that a message will have to wait in the queue? And if I have a finite buffer size, like that, what's the probability that a message will arrive when the buffer is full, and so the message will be lost, and you'll be losing packets? So the engineering problem is that you have a trade-off here between providing too much resources, in which case you're wasting money, or too little, in which case you're giving bad service, because that means that the messages are queuing up and you're losing some and you're having delays. So what you want to do is you want to be able to come up with formulas that are going to allow you to balance the provision of the resources with the performance that gives you. And in order to do that, these are the formulas you need. So the first thing you need to know is you have to describe the probabilistic, you have to give the probabilistic description of the arrival process, which is what we just did, and then we have to give the probabilistic or random description of the bandwidth requirement, which we haven't done yet, and then we have to put these together and see how this produces formulas that will tell us what the trade-off is between the design parameters and the performance that those things produce. So this is going to something that from an engineering point of view is very practical, but you can see describes all kinds of things. I mean, if anything that describes the cosmic questions about times, distances between stars in the universe, or times between decay of radioactive particles, or distances between cow patties on a cow path, that's got to be the most fundamental thing there is. So this is the secret of life right here. This is one of them. Got a couple of secrets of life here. So this is a very, very important philosophically, and obviously very important from a computational point of view, from a practical point of view. Okay, so now I've given two examples of random variables that are continuous, that are specific ones, the uniform and the exponential. And now the question is, well, it's still kind of theoretical, so now it's time to understand about simulation and try and understand how you would simulate this, compare it with the theory, and so you can see how all these things work. So we're ready to start homework number 3. So any questions so far? Okay, this is called a Poisson process. And a Poisson process, these are just names now, is a process in which the times between events are independent, identical, exponential variables. And so you can describe a Poisson process in various different ways. And one of the ways is to describe the times between the events. And that turns out to be, for our purposes, the best way to do it, the most convenient. But it's not the only way. If you go to the library, the internet, you type in Poisson or Poisson process, it goes on forever. I mean, there are literally shelves of books written specifically about the Poisson process or stochastic processes. Remember that the name of the course is Stochastic Models. For CS and E. The E isn't in there, but that's just because we didn't have enough space. Okay, stochastic means random, and processes like this are called stochastic processes. And in this particular one, is a special case, it's called the Poisson process. Other stochastic processes are ones in which, for example, the times between events are not exponential. There's some other model, some dependence or something of that sort. So the Poisson is the most basic one. It's the starting point. Now, this is a model because what we're doing is we're making a model of reality. This is our model right here. And then the theory comes when we change that model to a mathematical description, a theoretical description. At this point, it doesn't matter what the lambdas and the t stand for, as long as if this is the correct model, then this is the correct distribution function. And the fact that we're going to apply it for this particular case. This is going to be our primary example here. That's why it's for computer science and engineering, because that's what computer scientists and engineers are concerned with, is the design of systems like the internet, although it happens all over the place, in which the provision of resources and the configuration is something that is decided upon by an engineer or designer, but the purpose of the system is to respond to demands that are random. So that's the whole thing. Okay, so let's test this. So I'm going to erase this. Any questions? Okay, so now we're up to homework 3. So homework 3 is the first substantial homework. Well, maybe homework 0 was too, except that was supposed to be a review. So it'll take me a while to describe this, but let me start out. So this is homework 3. And it's called dumb exercise. And the dumb exercise title, that's not, what that is supposed to indicate is that, in a sense, this is dumb because all I'm going to do in this exercise is show you that if you simulate things like this, which you don't know how to do yet, that's part of the course, if you simulate them, which is a version of measuring things, then the theory works. Of course it works. It has to work because these things are all basically different viewpoints of the same thing. So in that sense, it's a dumb exercise. It doesn't mean it's easy. But the reason I'm going through this is a few years ago, this girl came into my office. She was taking this course and she was really upset. She was crying, really kind of tough. And so it turned out that the problem was that she thought that I was embarrassing her by calling this a dumb exercise, and she couldn't solve it. And so she was taking this as a personal affront, and I had to say that this was really a joke, and there was nothing personal there. So if anybody gets upset, dumb exercise is nothing personal, it's just a joke. Okay, so here's a dumb exercise. What it's going to ask you to do is this. It's going to ask you to consider 4 different cases. So you have case, and there's going to be 1, 2, 3, and 4. And in each case is going to be a random variable, which I'll call x. And in the first case, the x is going to be uniform, 0, 1. So most of the theory that's associated with this, you've already done. Then in the second case, the way it's given is it's given, a density function is given, but it's the density function for the exponential with parameter 2. In the third case, you're given the world's simplest one, which of course is the one that always causes people grief, which is that the probability that x equals 1/2 is 1. That is, this is a random variable that doesn't vary, but always takes the value 1/2. And the fourth case is just a discrete random variable, and its probability mass function is given. It says that the probability that x equals minus 0.2 is equal to 1/2, and the probability that x equals plus 1.2 is 1/2. So those are the 4 cases that you're going to look at. And then it's going to ask you to calculate things like the expected value, the variance, and the probability that x lies between A and B. And in our case, A is equal to 0.25, and B is equal to 1.35. And these are all the values that were assumed in homework 0, so that some of the arithmetic has already been done. You don't have to re-evaluate integrals again. And then in each of these cases, it asks you to calculate these things 2 ways. One is the theory, and the other is the simulation, the experiment. So now I got to discuss the simulation experiment, because that's equally important, maybe more important. And then we'll go back and fill in the pieces of the table. So what you have to do is you're going to have to do the theoretical calculations, most of which you've already done, and then run the code to see that simulation and theory agree, and draw some graphs to show that they agree. So I'll explain it. It was not a big deal, although it's probably the longest homework, maybe the hardest homework. It's not hard after you do it. It's hard because these are new concepts, so people tend to have trouble with this. All right, so it says, first of all, it's worth 40 points. Then it says, the following basic code generates 10,000 values of a random variable x and calculates the sample average, which is theoretically described by the expected value, the sample variance, and the fraction of sample values that are less than or equal to a half. Okay, so here's the first thing. It says, adapt this simulation program. You may use BASIC or any other language, and then you have to calculate these things. So when it says that the code I'm going to give you calculates the probability or the fraction of sample values that are less than or equal to a half, and then it says adapt. That means that instead of calculating the probability that the x is less than a half, you're going to calculate the probability that x lies in this region. So that means you have to change the code slightly. So there are always people who somehow or other can't figure that out. But that's why whenever I give you the code, I always give you the code that does something slightly different from what I want, and then that means that you can't just copy the code blindly. You have to realize what the instructions mean, and then change the instruction that does what you don't want it to do. Okay, so first let's go through the code here. So here's statement 100. Remember, I'm using BASIC because it's simple pseudocode, but you can change this to anything you want. So I'm going to put this in a loop, and I'm going to calculate this for values. So I'm going to calculate this 10,000 times, is what it asks you. So I'm going to say for I equals 1 to 10,000. And then I imagine that here's what's happening. I've got this urn, and the urn has in it the tickets. This is the population of X's, and each ticket has a number on it, and you reach into the urn and you pull out a ticket. And that represents a realization of the random variable. So in case 1, then you're going to draw a value from a uniform distribution, which means that you're going to, in effect, spin the dial. In case 2, you're going to draw a value from an exponential distribution. That's what we've just been discussing. In case 3, you're going to draw a value from the distribution that always takes the value 1/2, which means, of course, that every ticket in the urn will have the value 1/2. In case 4, you're going to have the urn in which half the tickets have a minus 0.2 and half the tickets have a 1.2. So in every case, when you're simulating a random variable, you keep in your head the picture that you have this urn with tickets in it. The tickets have numbers on them. Those are the values of the random variable, and the relative frequencies of the numbers in the urn are described by the distribution or density function or probability mass function of the random variable that you're trying to simulate. So in the first part of the course, these were all discrete. These tickets would represent the numbers that you got if you rolled 2 dice, or you picked a card out of a deck or something like that. But now, they don't have to be discrete. This is continuous, that's discrete, that's discrete. Okay, so we're going to do this 10,000 times for each random variable. So that's actually, in other words, you have to run the simulation, run this program 4 times. Now, the first thing I do is I reach into here and I pull out a ticket. So I'm going to write that this way. I'm going to say generate X. So that's the big question. How do I write an instruction that pulls a ticket out of the urn such that the fraction of tickets having a value less than t is described by the distribution function that's given? So this is a big question you don't know how to do yet, but just imagine you could. So you tell a computer, okay, pick a ticket from the urn. Now we have this value of the ticket. So statement number 200 says that S1 is equal to S1 plus X. Remember, I'm using BASIC here, so I don't have to worry about overhead. everything, all the variables default to 0 initially. So what I'm going to do here is I'm going to accumulate the values of x. So every time I execute this instruction, I'm going to replace the cumulative sum with whatever it was before plus the value of x I just generated. So when I get done, I will have added up 10,000 values of x. And then if I divide that by 10,000, I will have the average value, which I can then compare with the theoretical expected value. So that's the purpose of S1. Okay, now, next instruction is 300. And now I'm going to accumulate something in S2. And S2 is equal to the sum of the squares of the x's, which in BASIC you use a little caret to indicate square. I could have written x times x, same thing. All right, so here I'm going to accumulate the sum of the squares. So why do I want to do that? Because I want to calculate the variance. And the variance, remember, is the average of the square minus the square of the average. So here I'm going to accumulate the average of the squares. Then I'm going to sum up the squares. I'm going to divide by 10,000. That'll give me the average of the square. Then I will subtract the square of the average that I will have already computed, and the difference will be the variance, and that should agree with the variance that you'll compute from the theory. Of course, you still don't really know what variance means, why you want to compute that, but that will come when we go to these applications. Then statement number 400. Okay, so 400 says, if x is less than or equal to 0.5, then count it. Okay, so this is a phony instruction because what I'm doing here is I'm counting all of the x's that are less than 0.5, less than or equal to 0.5. If I then divide this by 10,000, I will get the fraction of x's that are less than or equal to 0.5, or the probability that x is less than or equal to 0.5. So the program is written to do that, but that's not what's asked for. What's asked for is to calculate not the fraction of x's that meet this requirement, but the fraction of x's that meet this requirement. So that means you have to change this instruction. So what you would say is, if x meets this condition, lies between 0.25 and 1.35, then you want to count it. And if not, you don't want to count it. So you count the number of x's that lie in this range. Then statement number 500 says, do it again, next odd. Okay, so I'm going to go through this thing 10,000 times, and then I'm going to print out my answer. So I'm going to print, and what I want to print is, first of all, S1 divided by 10,000. So that's going to be the average, because I summed all the x's. I'm going to divide by 10,000. There are 10,000 of them, so this is the average value of the x, which should be close to the theoretical expected value. Okay, the next statement, print. Now I want to print S2 divided by 10,000 minus S1 divided by 10,000 squared. So this is the average of the square, and this is the square of the average. So the difference between them is the sample value for the variance, which you want to compare with the theoretical predicted variance. Of course, they'll come out to be very close to each other. And then finally, if I wanted to calculate the fraction of x's that meet this requirement here, and count out how many of them there are, I just take that number, divide by 10,000, and that's my answer. Okay, so we've got several things to do. First of all, there's another part to the problem which asks you to draw some graphs, which means you have to calculate other values besides these. Just means adding a few instructions. And then what the assignment asks you to do is to calculate the distribution function of x for various values of t. So in other words, you're going to have to calculate the fraction of x's that are less than t for different values of t and draw a graph. and then compare that with the theoretical distribution function. That's the formula that you have. And then, of course, again, if you do it right, it'll come out to be very similar. But you have to draw your graph accurately, otherwise it doesn't make any sense. Then we have to worry about the actual theoretical calculation of these things, most of which has already been done, because I already did everything for case 1 and case 2. And case 3 and case 4 are too simple to even think about because they're discrete, even though that's, of course, what it gives everybody problems, because these things are more formal. Integral, there's a formula. These things were more vague because when we discussed them, it was more difficult to be mathematically rigorous than it was to just say, yeah, you're just adding things up. So you have to know what you're adding up in order to do these, but this is really simple. So the big deal here is, how do we generate the value of x? Okay? So any questions up to this point? So I'm going to start that question about how you generate x, but there are really then two big theoretical points in this lecture. One is the derivation and understanding of the exponential distribution as a description of the times between events in a Poisson process. That is, in a process in which events occur at random with no memory. And then the second theoretical part is how, given any required, any stated random variable that is described by its distribution function, how, knowing the distribution function, you can get the computer to draw numbers out of the urn such that the frequencies of those numbers are exactly what the distribution function prescribes. That is, how you generate a random variable with any prescribed distribution function. What that means is that any probability problem can be solved in terms of an estimate by writing a simulation. Because if you can take any probability problem and have a computer generate the actual values that the random variable takes, then any combination of those things, no matter how complicated, that's simply logic. It has nothing to do with probability. For example, we're going to write a simulation that will describe this queuing problem that I mentioned. That's the one where the messages arrive at random, and they have random specified distribution functions for their bandwidth requirements. And you want to know things like, on average, how long do the messages wait? And what's the probability that they wait? And what's the utilization of the server? And how likely is it that the messages will overflow the buffer? And lots of other things. But once I can express this in terms of two urns, one urn has the service requirement, the bandwidth requirement, and the other urn has the inter-arrival times, the times between these arrivals, which will be exponential in our case, then that means that I can reach into the urn and I can draw this value, that value, that value, that value, that value, that value. Now, if I had all these values, it doesn't make any difference once I know what they are, whether someone simply gave them to you or you measured them or they came from an artificial simulation. Once I have these, I can then take these values and run them through a template that describes the physical configuration that I'm trying to analyze, and I get my answers. So the probability part is removed once I know how to generate X. And the rest of it is just programming, or if you do it by hand, just boring record keeping. So for example, if you, in the operating systems course, you might have a question in which someone tells you when jobs arrived and tells you what their CPU requirements are and asks you what the average delay is. And if there's only 2 or 3 messages, then you can sit down and you can figure it out. You can trace it through. It's boring. And besides, it doesn't mean anything because it works only for that particular case. If you were doing a real case, of course, you wouldn't trace it through by hand. You would have some data, and the data, if they're to be realistic, would have to be things that follow the statistical or stochastic descriptions of the arrivals and the service requirements, and not just some numbers that someone put together. So the two pieces then are, one, how do you generate the random variable values that are the inputs And then the second piece, which has really nothing to do with this course, except that I want to use it to illustrate this, is the code that actually runs these values through the configuration, through the template, to give the final answers. And what you'll see when we do this is that for certain cases like this, which are interesting and important, the code is unbelievably simple. It's so much easier to do it in general than it is to do a particular case. Basically, it's this many instructions, and I can simulate this whole queuing problem. It's done recursively, so we'll get to that later on. Anyhow, this is where we are now. All right, so let me give you the algorithm, and then later I'll try and explain why it works. So, any questions up to this point? Nobody's asked me any questions, so as I say, I never know how to interpret that. Okay. So what I'm talking about is what's called the inverse transform method. And I'm going to repeat this a zillion times because this is we're now getting to the key, the heart of the course. This is the whole reason we have this course. Because everything up to now has been toy problems. And this is in the book, but it's in the book, it's in all the books, all the advanced books. But in advanced books, it's there in disguise. That is, it's usually stated in a way that's too mathematical to understand what it is unless you already knew it. And in the elementary books, they never state it, they just give you the cookbook rule. Or, if you use canned software, the software does it for you. But that's a cop-out to say, well, I can have somebody else do it. It's always dangerous when you have some software that does something for you which you don't understand what it does, and you just accept it. So that's bad. Okay, so here's what this is for. It's to use the random number generator that's in the computer, which you've already used in the birthday problem, to generate random variable values according to any, underline any specified distribution function. Okay, so that's the point. And there's an algorithm. So I'm going to state the algorithm briefly. Here's the basic idea. Suppose that the distribution function of the random variable that I want to simulate has a formula, capital G. So I'm going to draw it like an exponential, because if I'm going to draw something, I have to make it, if I'm going to draw a picture, I've got to draw a picture of something. So here's what the exponential would look like. But this is a typical distribution function. So I'm going to call this thing here G of U. So it's a distribution function. That means it starts at 0, it ends at 1, and it's non-decreasing. So there's what the exponential would look like. You already drew this graph for the exponential in homework 0. And now the question is, suppose that I have some formula. It doesn't have to be exponential, but this is what an exponential would look like. How would I generate a random variable whose distribution function is G? And the answer is that what you do is you ask the computer to generate a random number, which I'll call R. So this is what the random number generator gives me. You put the random number on the vertical axis and you project over to the curve and down, and you call the result X. So it's an inverse transform method, inverse transform, because I'm going backwards. I have this function right here. Instead of plugging in the x and getting the r, I'm going to plug in the r and ask what x that came from. Now, what the theorem says is this. It says that if the r is uniform between 0 and 1, then the x will have as its distribution function whatever this formula is. Okay, now as I say, I got to go over that. I'm going to prove it, and then you're going to actually see it, because that's what this homework is designed to do, to show you that if you do this, in fact, the values you get from the computer are going to agree with what's predicted from the formula. Okay, so what does it say? It says, ask the computer to give you a random number between 0 and 1. So that's supposedly uniformly distributed. That's what the computer is supposed to do. So the random number generator generates numbers that are uniform between 0 and 1. You already used that when you generated birthdays. Now, if in fact the random number can generate numbers that are uniform between 0 and 1, then by this method it can take those numbers and change them into other numbers, and the new numbers will have as their distribution function whatever formula you use for this curve, whatever g is. Which means that if the computer can generate numbers that are uniform between 0 and 1, it can in fact generate numbers with any specified distribution whatever. In other words, all you got to do is know this formula, and that will tell you how to get the numbers out of this urn that have that particular distribution. Okay? So let me write down what the theorem says. It says this. Let's say here is t, and then this thing would be g of t. And what I'm going to do is I'm going to prove that if r is less than g of t, then the x's that come out of this have g of t as their distribution function. So the theorem says this. Theorem. If r is uniform 0, 1, we can check and see whether it is, because that's up to the person who writes the random number generator to make sure that his r corresponds to flicking that dial. If r is uniform 0, 1, then the distribution function of x, that's what you're trying to find, the distribution function of x using this algorithm will be equal to g, whatever this formula is. So this seems abstract now, but it'll make sense later. And this theorem, let's see, let me write it here. Just if you want to look ahead, this is theorem 11.2, which is on page 476 in the book. So it's at the end of the book, and I'll put in parentheses, it's in disguise. So when you go and look it up in the book, probably won't look anything like this, but I'll explain why later. So here's another point. This obviously is one of the most important things you would have in a course like this, but you don't get to this until the very end of the book. If we covered the book from beginning to end, it would be a couple of years. All right, so homework 2 is due next time, and I'll start here next time. So download homework 3, because you should have it in front of you.